Hi everyone and welcome to another measurement and instrumentation class. Today's class we will continue with power measurements and energy measurements. In the previous class we did single phase and three-phase power measurement systems. Now today we're going to continue with power and energy systems. So the outline for the class is going to be what is power? You already know that. Power in DC and AC circuits, the difference between them. Power measurements and power instrumentations, such as watt meter. And energy, what is energy? Energy instrumentation, energy meter for single phase and three phase. Now, I've added this slide, and the reason that I included this slide is to show you how a single phase and a three-phase system signal looks like. As you know, three-phase, we have a 120-degree phase shift. But sometimes we need a higher volt, and for a single phase, or we just have a single phase sinusoid signal. But sometimes we need more than 120 volts for some appliances. Example for that is going to be electric stoves and dryers. For those, we use a 240, 220, 240 volt system. Now, the problem is the voltage that comes into your home is usually from one of the phases of a transformer. And the way that we increase that voltage, we don't actually use a three-phase system. The system that is used in a home is coming from a transformer, which has what we call a center tap system. So a center tap transformer, in the input you have a single phase coming from the left here, positive and in the ground and negative. But the output, you have three outputs. One is connected to the central part of the secondary winding, and one is on one side, the other one is on the other side. Now what this does, it creates two different signals, and these two signals are 180 degrees apart. So you have a 180-degree phase shift. Now when we have a 180-degree phase shift, what happens is you're going to have, when you add these two, you're going to have zero voltage, and at their peak you have two 120-degree voltage difference between them. So it's going to be a 40 volt system. So you can see here, and by the way, this is the effective or the RMS voltage is 120 volts. So from positive to negative 120, you have 240 volt system. So this is actually the way a 240 volt system works in a washer dryer. You have technically two phases that are 180 degrees apart, meaning they are going at the opposite direction at all time, and therefore it doubles the voltage from 120 to around 240 voltage. So your washer dryer is not actually three-phase, it's a kind of two-phase system. But some systems may have three-phase, but the problem is the majority of homes in the US don't have a three-phase, breaker. It's going to be very expensive. So they use a system instead of that, a two-phase system. Now, some power instruments and measurement tools for measuring DC and AC. For DC circuits, we have a multimeter, digital multimeter. We can use galvanometer. In AC, we have three-phase systems, high-frequency power measurement systems. And for energy measurement, we have DC circuits, AC circuits, and some examples are power and energy measurements and motor drives. We already mentioned a three-phase system using 2-watt meter system, 1-watt meter, and so on. But another concept that we have in electricity is energy as well. And we already know that power in electric system is measured in watts. The SI unit is all watts. And 1 watt is 1 joules per second. Okay. Another term that we commonly use is 1 kilowatt, which is 1,000 watts or 1,000 joules per second. Power can be defined as the time rate of energy transfer or energy dissipation and load, and power is the rate of using or supplying energy. Power is this is an instantaneous term. Energy is what we consume in a time frame. So when we say this motor is 2 kilowatts, meaning at each moment it's consuming 2 kilowatt, and that's usually the rated number, the maximum that you can consume. And as you know, power is current times the voltage difference, or P is equal to VI. This is an important slide. Power can be negative or positive. If the system is consuming power or absorbing power, the P would be positive. So if you have a heater, if you have a motor, the power would be positive. And if we calculate power and power is negative, then the system is generating power. So a solar system, a PV photovoltaic system has a negative power. A generator has a negative power. Battery has, if it's giving the power, it's having a negative power. When you're charging it, it has a positive power. Now, power in DC circuits, as you know, could be written in a different way. P is equal to IV, V is equal to IR, so I can replace V with IR. Then P would be equal to I square R, or V square over R. Power is in watts, current is in amps, and resistance is ohms, and voltage is in volts. We have different ways to connect a watt meter. So to calculate power, as you know, again, we need to measure the voltage and the current. So we need a voltmeter and a ammeter to create a wattmeter. Ammeters are connected in series. Voltmeters are connected in parallel. So there are two different ways that we can connect them. We can connect the voltmeter to the load and the ammeter in series with all of that, or we can use the ammeter in series with the load and connect the voltmeter to the ammeter and the load. Now, if we do the one on the left side, or A, figure A, the ammeter is measuring both the current passing through the load and the current passing through the voltmeter. If we had an ideal voltmeter, this wouldn't be an issue. But as you know, we don't have ideal voltmeters, so there would be some current passing through the voltmeter. So now I of the ammeter is measuring both I of the load and I of the voltmeter. So we have a little bit of error over here. Power is actually showing the power that you're measuring is showing a little bit of power that it's going into the voltmeter as well. Another way is to measure the voltage combination of the ammeter and the load. Again, here, voltage of the voltmeter is calculating voltage of the ammeter plus voltage of the load. Again, an ideal ammeter, the internal resistance is 0, therefore the voltage drop is 0. But for a non-ideal ammeter that we have here, the internal resistance is not 0, therefore you have a little bit voltage drop on the ammeter, and therefore when you're measuring the voltage, you're measuring both the voltage of the ammeter and the load. So one way to find out how much voltage and current is just to switch them and do the measurements, and you can see how much the ammeter and how much the voltmeter are consuming power. But these are the only two ways that you could do that. Now, digital wattmeters are used to measure power. They will measure both the current and voltage. Their advantages are they are high resolution and they have good accuracy. There are several techniques like multiplication of signals. An electronic multiplier is an analog system which gives as its output a voltage proportional to the power indication required. and it has an A to D conversion, analog to digital conversion. Another type we have is called a Hall power meter. A coil generates magnetic field, which is proportional to load current. The sensor excitation current passes through R1 and is proportional to the load voltage. And the Hall voltage is proportional to the load power. The problem with this system is offset and linearity. And again, this could measure at the same time the voltage and current. Therefore, you can measure the power going inside the system. Now, again, linearity, why do we have offset and linearity? Because of these mechanical parts that we have in the system, in the Hall sensor itself. If the power goes too high or too low, you're not going to have a linear response. And the offset also, obviously, because of the mechanical parts, and you have hysteresis in the system, so a couple of different errors in the system. Now, first example, very simple example. How much power is used in a circuit which is 110 volts and has a current of 1.36 amps? P is equal to IV, so 1.36 times 110 gives us 150 watts. Now, second example I want you to solve. And one thing that I forgot to mention, energy E is measured in watt hours, or PT. Energy is the amount of energy, power that you measure in a certain time. And usually we measure it in watt hours or kilowatt hours. This is the term that is used by the electricity company, the power company like EXO. They actually measure the amount of power that you consume in 1 hour. So, for example, if you have a washer dryer that is turned on for half an hour and it's 4 kilowatt, then your power consumption for that would be 2 kilowatt hour, because you use the washer dryer for half an hour, 4 kilowatts times half, it's going to be 2 kilowatt hour. This is the way that they measure it. And the power generation is the same as well. When they want to pay a generation company, they measure the kilowatt hour and they do it per year. So, for example, they would say this wind turbine has generated 10,000 megawatt hours per year, meaning every day it generate like maybe 1 kilowatt, but it did it for 365 days. And when you multiply it, for example, this is just rough estimation. Obviously, wind turbines can't and don't work 24/7, but we measure the total amount of energy produced, not the instantaneous power. So the nominal power of a wind turbine could be 3 megawatt wind turbine, but it almost never works at its peak output. You have to have ideal conditions to produce 3 megawatt for an hour. Usually it's around like 60, 70, 80% of that. So you're producing 2.42 megawatts for an hour. And again, it depends on the wind situation and a lot of different factors. Now, I want you to solve this. The work done by a heater is 100 joules for 4 seconds. Find out the electric power of the heater. And by the way, for this particular case, imagine that our power or work, energy or work, is PT and T is in seconds. So I want to find the power per second. I'll give you a few minutes to think on this. And Did anyone find the answer? What is it? Sorry? Yes. Yep. Okay. So given the work done by heater 100 joules, time taken by heater is going to be 4 seconds. Therefore, the electric power of the heater would be P is equal to W over T, which is 100 over 4, 25 watts. Easy as that. Yeah. Second example, the electric power of the electrical bulb is 50 watts. Then at how much time required to the electrical bulb to perform the work of 150 joules?
Is it still in seconds or is it in
Seconds. I've added a few more examples as well, which again is going to be pretty easy. Now, we have already done the power measurements in a DC direct current. The power is P equal to VI, and total power is going to be the voltmeters reading times the ammeters reading if we have an ideal situation. In one-phase AC circuits, the wattmeter consists of two coils, the current coil and the potential coil. The circuit diagram is displayed in this diagram here. Total power would be the wattmeter reading, which is going to be VI cosine of phi. This is for an AC system. From this, power factor can be measured the cosine of phi, which is P over VI. And you can see both the current coil and the potential coil in the system. Now, in a 1 wattmeter method, we already measured this. We must have a balanced star system to be able to measure the total power of a 3-phase system using 1 wattmeter system. And the total power would be 3 times the wattmeter reading. So if the wattmeter shows 10 kilowatts, the total would be 30 kilowatts. Now, for a 2 wattmeter method, and we calculated this as well, if we have 2 powers measured, the total power would be equal to the summation of wattmeter number 1 plus wattmeter number 2. Now, the 2 wattmeter method is the most general for calculating power in 3-phase because it can be employed for both balanced and unbalanced systems. So we don't necessarily need all the loads to be equal. They could not be equal. And they could be connected in either star or delta. For 1 wattmeter method, it must be only in star and it must be balanced. The current coils are connected to any 2 of the lines, and the voltage coils are connected to another line. The one with no current coil connections, as displayed in the below, and you can see how they are connected. So we measure the voltage between the one that has a current meter with another line that doesn't have it. So you can see between R and V, or S and V. But the voltmeter must be connected between the ones that don't have the current meter connected to them. We don't care. It could be balanced loads, or it could be used for both, for load and source. You can use it to measure the. Thank you for the question, by the way. Good question. This could be used for measuring generation or load. Technically, we are measuring generation because, but yeah, it could be used for both sides. By the way, this is only measuring, when we are measuring this is measuring the average power, the real power. If you wanted to measure the reactive power, you use the equation that, do you remember, square root of 3 times P1 minus P2 over P1 plus P2? That gives you a tangent of phi, and tan inverse of that phi gives you phi, and cosine of that phi gives you the power factor. And using that power factor, you can measure the reactive power. And the apparent power and so on. Now, power in an AC circuit, we already had this equation. The reason that I mentioned this because one of the students had a question in the previous class. Instantaneous power P is equal to VI, which is V max sine of theta times I max of sine of theta times phi. By the way, this is multiplication, it's not x. And for that, it's going to be V max I max sine of theta minus phi. Now, I can write this in another way. The mean power, the average power, is going to be 1 over 2 pi. And this is for just sinusoid. By the way, if you have a different type of AC signal, it's not going to work. This is not going to work. Which is going to be the integral of 0 to 2 pi, V max I max sine of theta minus phi. And what is phi? Phi is your phase shift, the phase angle between the current and the voltage. Therefore, it gives you V max I max cosine of phi. In other words, we can do VI cosine of phi. Why? Because V max I max, Vm, what is Vm equal to in relation to VRMS? Am I correct? Yes. So if I connect, and what is IM? It's going to be IRMS over square root of 2. Yes. So if I multiply these two, what do I get? I would eliminate the divide by 2, so I get VI cosine of phi. Now V and I are RMS values of voltage and current, and to calculate power, we should know the power factor of the load in AC circuit. Power factors are usually stated as leading or lagging to show the sign of the phase angle and the current with respect to the voltage. Now, current B lags the voltage by 45 degrees in this example. So the vector points down and to the right. So you can see it below. Current, and if we have current A is leading by 45 degrees. Again, the red one is the current and the blue one is the current, and the black in the middle is our voltage. Current A is leading with 45 degrees because it's ahead of the voltage, and current B is lagging, it's behind the voltage at 45 degrees. So leading, again, it means it's happening 45 degrees ahead of the voltage. So it points up and to the right. Since the peak current are 1 amps, the RMS currents would be 0.707 amps. Now, we already went through this. The real power, let's solve an example. The real power is 700 watts, and the phase angle is 45.6 degrees. What is the apparent power? We first find the power factor, which is going to be cosine of 45.6 degrees, gives us 0.7. The apparent power is 0.7 divided by the cosine of 45.6 degrees, or the power factor, which gives us 1000 volt amps. Just a quick reminder that power factor is equal to power over the apparent power, real power over apparent power. In other words, apparent power would be real power over power factor. And what is the relation between reactive power? So here I want to find reactive power. I want you to find Q. What is Q here? I'll give you a few minutes to think on this. We want to find reactive power, Q. One way to do it is S squared is going to be equal to Q squared plus P squared. In other words, Q squared is going to be square root of S squared minus P squared. I'm sorry, Q. Yes, and there's another way, easier way to do it. Q, we already know the degree. So sine of phi is equal to what? What is sine of phi equal to? No, in terms of, it's going to be Q over what? S. So you can find sine of 45 degrees. You already have S, you can find Q. There's another way to find it as well. What is the tangent of phi? Q over P. Yes. So you can find tangent of 45.6 degrees, which is around 1, close to 1, and then you can find Q. Now, I want you to calculate this. What is Q if we calculate these? What is sine of 45.6 degrees? 0 point what?
7.
Sine of 45.6 degrees is
0.7.
714. So, and this multiplied by S gives us Q. So Q would be 714. Now, what is tangent of 45.6 degrees?
1.02.
Okay, so 1.02 times P. How much was P? Gives us 740. Yes? So you can see any way that you solve it, and if you solve it using that, you're going to get all of them, get the same question. So if you have the angle phi, the easiest way is to use the sine or cosine of theta, or
And
tangent.
One would be the most accurate finding.
You're going to have all of them gives you the exact same. Yeah, gives you exact same. Now, the power operating of a motor is usually expressed in power units called the horsepower. And 1 horsepower, or HP, is 746 watts. You're going to see this a lot in power systems. We usually measure electric power machines and motors in horsepower. Usually we say like with 3/4 or half horsepower, or 1 horsepower, or 2 horsepower. And for example, if the motor is 2 horsepower, it means it's 1.592 kilowatts, for example. Okay. So 1 horsepower is less than 1 kilowatts. If an engine is 770 kilowatts, it's around 100 horsepower, something around that. Now, electric motors have a lot of advantages compared to internal combustion. What an advantage is that they have instant torque. And so usually, but the thing is, because we measure everything in the older systems, it was always horsepower, so they convert watts and horsepower most of the time. But if you have electric motor in an EV that says it's 70 kilowatts, it's around, again, 100 horsepower, so equivalent to that. And the torque is much higher. Usually it's around like 150 to 100 Newton meters. Now, electric motors and other systems have an efficiency or mu of operation, which is going to be equal to the efficiency as P out over Pn times 100%. Some examples. We want to calculate the power for a 12-volt battery supply at 250 amps to start a motor. What is that going to be? And we want to measure it in horsepower, by the way, HP. So what is it in horsepower? Yes. So the total power VI is going to be 12 times 250, which gives us 3,000 watts or 3 kilowatts. And if we divide that, 3 kilowatts divided by 746, or 3,000 divided by 746 gives us 4.02 horsepower. We want to find the current drawn from a 115 volt line by a DC electric motor that delivers 1 horsepower by assuming 100% efficiency of operation. I want you to solve the second and the third question as well. I'll give you a few minutes to think on this. Again, I'm just going to write 1 horsepower is 746 watts. Did you solve it? Do you need more time? Okay. So for the first one, because the efficiency is 100%, the input power is equal to the output power. We have 100% efficiency. And how much does the power it delivers? It's 1 horsepower or 746 watts is delivered to 115 volts times the current. So I would be 746 divided by 115, which gives us how much is it?
6.5.
6.5 amps. Now the second one, we want to find the efficiency. To find the efficiency, we need to find the output power to the input power. Now the output power is 2 horsepower, so 2 times 746. And the input power is 19 times 100. So 2 times 446 gives us 1492. Am I correct? I'm doing it on top of my... And over 1900, which is, how much is it? Yes, 78.53%. Thank you. Which is very low actually for a DC. Electric motors can go up to 95, 96. I mean, like very, very sophisticated ones are 98. Usually they're like between, very bad ones are 85, 80, like 90%. Normal ones are 92, 93%. So 78 is a pretty, low efficiency. Internal combustion is around 16 to maximum is like 30% for, turbojet engines, so on. Power measurements. So a wide variety of instrumentation and transducers for the measurement of power in AC/DC circuits are used. Important primarily for the testing, monitoring, and maintenance of the energy supply network and electrical equipment. It's required in high frequency and low power circuits. A wattmeter is suitable use for the power meter measurement in DC and AC systems, which will give the same angle of deflection for a given power. Now, why wattmeters are needed? Ammeters measure load current IL and there is voltage drop VA across the ammeter, and we already know VL is V minus VA, and PDC is going to be VLIL, which is V minus VAIL, which is VIL minus VAIL. So the power measured by the meter is the power consumed by the load plus the power loss in the ammeter. The product of ammeter and voltmeter does not give correct power consumed by the load. Now, if the voltmeter, so again, different combinations, if the current meter is connected directly at the load, the voltage that we are measuring is measuring the voltage of the ammeter and the load. So we have a little bit of, and we don't have an ideal ammeter. Now, if the ammeter is connected before the voltmeter and the load, you're measuring the current of both the voltmeter and the load. And since we have a non-ideal voltmeter, the input impedance is not infinite. You have a little bit of current passing through the voltmeter. So if the voltmeter shifted across the load to measure the load voltage, it measures VL correctly, but ammeter measures current I, and that I would be IL plus IV. So the DC power would be VL, IL, and IL is I minus IV. Therefore, it's going to be VLI minus VL IV. Therefore, the power measured by the meters is the power consumed by the load plus power loss in voltmeter. Therefore, the power measured is higher than the power actually consumed by the load. Now, we get to wattmeter errors. There are different errors in a wattmeter. First one is the error due to inductance of pressure coil. Inductance of pressure coil may cause an error in the wattmeter reading. The instrument gives high reading on lagging power factor and low readings on leading power factor and true power. Pressure coil inductance causes a wattmeter to read more power than actual. To reduce this error, capacitance is connected in parallel with PC or the pressure coil. But the thing is, this only works when you have a lagging power factor, for example. It doesn't work when you have a capacitor. Another way to counter this error is just use a digital voltmeter, ammeter. But these digital ones are very sensitive to very high voltages. They are not usually used for ultra high voltages. And they are not passive like these, the ones that have pressure coils. They are active, meaning that you need an external source of power, like a battery or a DC, to measure high voltage AC. And if you run out of power or something happens to that, you can measure the output powers. So again, the reason that this happens is because if in the system we have reactive power, that reactive power is gonna reduce or increase the amount of power that coil is showing, because the coil itself is like inductance, and it's like adding to the mix of the reactive power. Another type of error is due to capacitance of pressure coil. The wattmeter reads less power. Both inductance and capacitance are present in the pressure coil circuit and therefore cancel the effect of each other. If the capacitance reactance is XC, the inductive reactance is XL in the pressure coil circuit, then the error will be completely eliminated if these two are equal. If they are not equal, and that's the problem, we don't know what the power measurement is. Sometimes it's the reactive power is higher, sometimes it's lower, sometimes it's positive, sometimes it's negative, and sometimes it's zero. We just have pure power. Now, another type of error that we have in these coil type galvanometers and voltmeters and power wattmeters is the alternating magnetic field, which creates what we call a eddy current. This actually alternating magnetic field of the current coil induces eddy currents in the solid metal parts nearby the current coil. So it magnetizes the whole thing, and then you're going to have an error in the reading. These eddy currents set up their own magnetic field and thus alter the magnetic and phase of the magnetic field, causing deflection. Thus, the error is introduced in the instrument reading. And another error is error due to power loss in pressure coil or current coil, error due to method of connection as well. So there are two methods of connecting wattmeter in circuit: measurement of power. In one method, the pressure coil of the wattmeter is connected on the supply side of current coil, whereas the second method, the pressure coil is connected on the load side of the current coil. In other words, in one method, you're connecting the ammeter before the voltmeter, and the other method, you're connecting the voltmeter before the ammeter. In one method, in the former method, the wattmeter reads the small copper loss, I square RC, in addition to the load power. Wattmeter reads W plus I square RC. In the second method, the wattmeter reads W plus I square P R plus RP. So first method is adopted for measurement of power in circuits carrying small currents, while the latter one is adopted for measurement of power in circuits carrying large currents. Now, these show some examples of, how we connect them to the supply side. So in this method, you can see that the current coil is connected to the load, and the voltmeter, this is technically the voltage of the supply, is measuring both the voltage loss in current coil and the load. Now, the voltage coil is connected to the supply side, as you can see directly, of the field coils, so that only the load current flows through the field coils. So you only have this current, which is actually to the load. However, the voltage applied to this series connected moving coil and multiplier is E plus EF, which is this voltage plus this voltage, the load voltage plus the voltage drop across the field coils or the current. Now the wattmeter indicates load powers plus an additional quantity, or EFI, In the high voltage circuits where the load voltage is very much larger than the voltage drop across the field coils, the error may be insignificant. Insignificant. In low voltage conditions, this error may be serious. So if you have a high voltage, we don't care about it. It's negligible. If it's a low voltage, then that creates a problem. The other way to connect it is the opposite. You need to connect the voltmeter in parallel with the load directly and the current coil in series with both of them. Now this problem this one has a problem of measuring the current both passing the voltmeter and the load, but the voltage that the voltmeter is measuring is exactly the same as the load. So the moving coil or voltage coil circuit is connected in parallel with the load. The field coils pass the currents, the sum of the load current and the moving coil current. This results in the wattmeter indicating the load power plus a small addition quantities, again, which is the voltmeter's power, where the load current is very much larger than IC. This error may be negligible. In low load current situations, the error may be quite significant. Again, if you have a high power situation, negligible. Low powers, it's going to create some power problems. Another types of error in these analog wattmeters, first, because they have mechanical parts, is the error due to friction. The friction error becomes relatively important in such an instrument due to availability of small deflection torque. Then we have error due to heating. Obviously, this error is mainly due to pressure coil circuit, which carries a current proportional to the voltage across its terminal and inversely proportional to its impedance. Such an error is usually very small. Again, because you have a little bit of resistance, it creates heat and it dissipates that and you have error. And finally, we have error due to stray fields. External fields may cause serious errors in the ordinary types of non-static dynamometers unless shielded, and we usually shield them with a Faraday cage. So it acts like a big antenna. You have magnetic fields coming to it and has a little bit of effect on the coils, the magnetics, either by means of an iron case or by laminated shields as well. And this actually shows an example of a wattmeter. And you can see that it's measuring, yes, the power. I think it's enough up to this point. We're going to continue with energy measurements in the next class. We don't have enough time to complete this part. I will post the solution for the exam by this weekend, and we're going to have another set of homeworks posted this weekend, but you're going to have 2 weeks. So I don't want to ruin your spring break. You're going to have until not that week, but 2 weeks from now, for at least 14 days or 16 days, something like that, to complete that. I'm sorry? I think this one is, it says energy and power. It doesn't show L or something. It's just energy and power. I think it's L9, but if you look at it, it just says energy and power.